In this video we will show how the force-speed diagram with the road resistance curve for a flat road can be used to graphically determine what traction force is required. What we will show is a graphical representation of the vehicle model and its force functions. The vehicle model needs values of the vehicle parameter in order to calculate the force values. In this example we assume a vehicle with these parameters. These are, by the way, fairly typical for a mid-sized car. First, we assume that the vehicle shall keep a constant speed while driving uphill. The speed is 70 km per hour, so that is the speed at which we read the force required for overcoming rolling resistance and aerodynamic forces. In this case, 330 Newton. The road gradient is plus 5%, leading to a gradient force of 735 Newton. And since the vehicle shall keep a constant speed, the acceleration is 0, and then the required net force is also 0. That results in a required traction force of 1048 Newton. Now we analyze the same vehicle accelerating in the same uphill gradient. The speed and the gradient still are 70 km per hour and plus 5%. Now the vehicle shall accelerate 0.5 meters per second square, and that requires a net force of 750 Newton, which is added to the other forces. In this situation, the required traction force is 1798 Newton. Similarly, if the vehicle shall decelerate on the same uphill gradient, we have the same running resistance and gradient force. Now the acceleration is minus 0.5 meters per second square, leading to a net force of minus 750 Newton. Adding this to the other forces, we get this operating point of the vehicle powertrain. And the required traction force is in this situation only 298 Newton. We will now analyze the same vehicle accelerating on a downhill gradient. This time the speed is assumed to be 100 km per hour, leading to the running resistance of 486 Newton on a flat road. The gradient is now minus 5% and the gradient force minus 735 Newton. Assuming plus 1 meter per second square acceleration require a net force of 1500 Newton, leading to a traction force of 1252 Newton. And finally, we will see what happens if the vehicle shall keep the speed constant on this downhill. Running resistance and gradient force remain the same. There is no acceleration and no net force, leading to a required traction force of minus 248 Newton. This means that the driver must brake to keep the vehicle speed from increasing on the minus 5% gradient. This example shows how the traction force can be calculated from the running resistance curve for a flat road, adding a force proportional to the road gradient, plus the net force which is proportional to the required acceleration. Next we will show how it is easier to interpret the effect of a force if it's divided with the vehicle weight. Vehicles of different size will require different traction force in the same driving situation. Since the variation can be rather big even for vehicles of similar type, it is sometimes difficult to just look at the maximum force a powertrain can produce and from that judge whether it's a strong powertrain or not. For example, on a small sports car, a maximum powertrain force of 10,000 Newton can provide a very good performance, while the same 10,000 Newton on a big van is only sufficient for a medium performance. Since most of the forces are proportional to the vehicle mass, the performance can be more easily interpreted if we look at the powertrain force divided by the vehicle mass. Net force, which determines acceleration, is proportional to vehicle mass. So is gradient force and rolling resistance force. The only force which is not proportional to the vehicle weight is the aerodynamic resistance. Since the acceleration force and gradient forces are much bigger than the aerodynamic forces, the normalized force value says rather much about what acceleration a vehicle can achieve and what gradient it can climb. 1 Newton per kilogram corresponds to 1 meter per second square acceleration, or about 10% gradient. Notice that the unit Newton per kilogram is the same unit as meters per second square, just expressed in a different way. So if you need to make a very quick estimate of the maximum performance of a powertrain, just calculate which normalized force it can produce, and that will tell you roughly how quickly it can accelerate and what gradient it can climb. To summarize, we can say that the vehicle model is used to calculate the traction force required in a specific driving situation. The driving situation is described by the 3 input variables: vehicle speed, vehicle acceleration, and road inclination angle. Now we also have showed how we can illustrate the vehicle model graphically based on the running resistance curve on a flat road, to which we add the gradient force and net force to get the required traction force. Thank you for watching. Click next to practice how to determine the traction force.